Assalamu alaikum, my dear student. How are you? Today, I'm here with a very important lecture of alkyl halide. It's a part two of the reaction of alkyl halide, which is elimination reactions of alkyl halide. Let us see what we will discuss in today's lecture. We will discuss the elimination reaction, what are elimination reactions are generally. Then we will focus on dehydrohalogenation. Then our target will be the E2 and E1 reaction. And finally, we will try to understand that what is the competition between elimination and substitution reaction, right? So let's begin. First, we should know, or we should try to understand what is elimination reaction is. It is a general reaction. I'm not writing here the alkyl halide. I'm just focusing here to show you that how elimination occurs. Elimination reaction always occur with adjacent carbon atom. Here you can see it's a simple hydrocarbon, and Y and Z could be any different. In case of course, alkyl halide, one could be hydrogen and one could be the halogen. And when these two atoms remove, we have a corresponding alkene. And by this way, we have basically the elimination reaction. You can see here, I wrote here that two fragments of a molecule are lost from adjacent carbon atom. This is basically the adjacent carbon atom. And definitely we have the multiple bond. Multiple bond means that alkene or alkyne depend on the removal of the adjacent atom. Now let us discuss what is dehydrohalogenation. Definitely, reaction of alkyl halide with strong base eliminate hydrogen halide, which is generally known as dehydrohalogenation. For example, it is 2-bromopropane. When we react with sodium ethoxide in ethanol, this strong base first remove the proton, which ultimately result in the removal of this halogen to give you this corresponding alkane. This is basically known as the elimination. Let us see some more example. For example, here you have a 2-bromo-2-methyl propane, and once you treat with a strong base like sodium ethoxide, you have basically a 2-methyl propene in a very high yield, 91%. For example, in the third example, we have a bromo alkyl, means 1-bromo alkyl, and means it could be any carbon chain. It's a primary alkyl halide. And once you treat with this strong base like potassium, tertiary BuOK will give you the corresponding alkene by the removal of hydrogen from the beta carbon and this halogen. Okay, now let us see in more detail about the dehydrohalogenation. What happened in actually in dehydrohalogenation? This is simple alkyl halide. And you can see this carbon bonded with the halogen. And of course, halogen is the functional group. That's why this carbon is basically known as the alpha carbon at which halogen is directly attached. And next carbon adjacent to this halogen is known as the beta carbon. And of course, the proton or the hydrogen bonded directly with the beta carbon is known as beta proton. So what happened? Of course, this halide is a living group, and this is alpha carbon, and this is beta carbon, and the proton is the beta hydrogen, as I explained. Now, what happened? Once you treat with strong base, a strong base always remove the proton from the beta carbon, like in this way. Once this base will remove the beta proton, what happened? Generally, this bond will collapse, and which result in the removal of this halogen, like in this way. Okay, you have a basically corresponding alkene, of course, salt and a corresponding butanol or alcohol as well. Okay, uh, in elimination reaction, we generally use some special type of the bases, and these bases actually give you the corresponding alkene. And let us see that how we can synthesize these strong bases. For example, if we react potassium hydroxide and dissolve in ethanol, base will remove the proton from the ethanol and will give you the corresponding ethoxide. Or generally, you have any strong base and you dissolve in a corresponding alcohol, base will remove the proton from the alcohol and give you the corresponding alkoxide. For example, I wrote here the alcohol treated with the base remove the proton and give you this alkoxide. This alkoxide is basically the strong base if it is small in size. These are two other methods by which we can synthesize alkoxide base, for example, oxidation and reduction of alcohol with metallic sodium. You will also have the corresponding base. For example, this, of course, this is basically a oxidation of sodium is losing the electron and this is gaining the electron. That's why it is having a negative charge. So you can see here this 2 mole of ethanol will give you 2 mole of corresponding ethoxide. Second one, how we can synthesize the ethoxide base which is used in elimination reaction. For example, this is ethanol, 1 mole of ethanol. When you treat with sodium hydride, this hydride remove this hydrogen to give you the hydrogen and this sodium combined with the ethoxide. You will have basically an alkoxide or sodium ethoxide. This is of course two important method to synthesize corresponding alkoxide base. All right. Let's begin. Some other common base and the solvent pair used in dehydrohalogenation or elimination reaction. For example, potassium hydroxide when we use in ethanol to give you ethoxide, or sodium ethoxide in ethanol. You will also have this combination as well to give you a strong base pair. For example, the third one, potassium tertiary butoxide, very important, very famous in tertiary butanol, and this butoxide or tertiary butoxide will act as a strong base. The alkoxide always prepared in excess of alcohol, thus the unreacted alcohol becomes the solvent for the alkoxide base. That's why we have basically similar pair of the alcohol as well. Okay, this is how I showed the synthesis of potassium tertiary butoxide when a tertiary butanol treated with the potassium. This potassium, if of course this is the acid base reaction or the oxidation reduction. One will oxidize and other will reduced. So hydrogen will eliminate to give you the 2 moles of potassium tertiary butoxide like in this. Now let's start the E2 reaction, which is a very famous reaction in elimination reaction. What is E2 reaction? As the name suggests, E2, it means elimination. 2 means 2 molecule or the bimolecule. Just like the similar reaction with the nucleophilic substitution bimolecular. Mean in this case, 2 molecule is taking part in a single step. Let's see. This is basically an alkyl halide. In this case, I'm using a secondary alkyl halide. Okay, you can see this bromine is bonded with the carbon and this carbon is bonded with the 2 carbons. So that's why this is basically a secondary alkyl halide or 2-bromopropane. Okay, this strong base remove the beta proton from the beta carbon, which ultimately result in the removal of this halogens. You can see here what happened next. We have basically a transition state. Simultaneously, a bond is established between this ethoxide and the hydrogen, which is basically removing. And a partial bond is being developed between these 2 carbon to give the corresponding alkene, which result in the removal of basically this bromide ion. Okay, and ultimately a carbon-carbon double bond is fully formed, and the other product are ethanol and the bromide ion. This is the new pi bond is being formed during this reaction. Okay, now what favors this E2 reaction? The free energy diagram. You can see here the free energy, or we can say the energy consumed to convert the substrate into the product is very much low. This is very kind of favor reaction. So generally E2 reaction favored with the strong base once you are using a primary or the secondary alkyl halide with this small and the strong base. Okay, so E2 transition or the reaction has just one transition state generally. All right, and thus we can say that the reaction rate depend on the concentration of both alkyl halide and the concentration of the nucleophile or the strong base, vice versa, whatever. Sorry, the base ethoxide, not the nucleophile. Nucleophile is in the nucleophilic substitution reaction. So the overall rate is the second order, or we can say this is E2 is basically a bimolecular reaction. Okay, now if you have basically an alkyl halide and both side definitely, if you have a secondary alkyl halide or the primary alkyl halide, you have a two different type of hydrogen, beta hydrogen. These two different type of beta hydrogen may result in the formation of two different alkene. Let us begin here, or let us see here. This is, you can see 1, 2, 3, 4. At carbon number 2, we have the bromo. At the same time, at carbon number 2, we have the methyl. So the name will be 2-bromo, 2-methyl butane. Now, at carbon number 2, you have this methyl. This methyl is a CH3. And each hydrogen definitely with respect to this carbon is a beta carbon, because this is beta carbon. And this beta carbon have the hydrogen which is known as the beta hydrogen, right? Beside this carbon on left side we have a CH2. This carbon is also known as beta carbon. This compound has two type of beta carbon. Now you can see here this CH2 has only two hydrogen, while this CH3 has three hydrogen, and both hydrogen are beta hydrogen. But for the sake of the to make the difference, I just name hydrogen A and hydrogen B. Keep remember, both these hydrogen are beta hydrogen. Just to make the difference between them, we are just giving the name as hydrogen A and hydrogen B. Now, why I gave the hydrogen A and hydrogen B, and I wrote here that the two different type of beta hydrogen, you can potentially form two different products. How? Let us see. This is one way. Once the strong base eliminate the hydrogen A, of course, this is beta hydrogen, and this hydrogen once collapse and remove the halogen, you have this product. And what is this? This 2-methyl-2-butene. And this is trialkylated alkene. You can see this is methyl, this is methyl, this is methyl. So three methyls are attached with double bond. Or this is most substituted alkene as compared to the second one. How we can explain this? Let us begin. Once base remove this hydrogen B, what happened? This bond will collapse, and which will result in the removal of this halogen to give you this alkene, which is 2-methyl-1-butene. And you can see this alkene, this is the CH2, and this is of course a carbon, and you have two alkyl group. So this alkene is the dialkylated, and this alkene is the trialkylated. So according to this rule, the most substituted alkene are more stable. So this is how basically a Zaitsev rule apply once you have a two different type of hydrogen in case of elimination reaction. Let us see the explanation. When, for example, we have a small base, for example, sodium ethoxide or the hydroxide, the major product will be the more highly substituted alkene, or we can say this more highly substituted alkene is the more stable. For example, the previous one, as I mentioned, this is the same case when you have a 2-bromo 2-methyl butane and you have the chances of two product, as I mentioned in the previous slide. This is the trialkylated alkene and the second one is the dialkylated alkene, and you can see the percentage yield. The trialkylated alkene was synthesized in 69% yield, while dialkylated alkene was synthesized in 31% yield. And that's the basically the set this rule says that the most substituted alkene is the most stable one. Okay, one more example. This is 2-bromo pentane. Now, what happened once you use the strong base, of course, this CH3 and this CH2, you have a two different type of beta hydrogen. Okay, this is a CH3 and this is a CH2. And of course, once the proton removed from this one, you will have a mixture of cis and trans alkene. Both are 2-pentene. 51% you have basically a trans alkene, Y trans, one up hydrogen, one down hydrogen, and 18% you have a cis alkene. Beside this, you have and both of these alkene are dialkylated alkene. Similarly, you have a monoalkylated alkene. Why mono? Because of the double bond. On left side, you have just one alkyl chain, while uh, on right side of the double bond, there is no alkyl chain. That's why this alkene is known as monoalkylated alkene. And the concentration or the percentage yield of this alkene is just 31%. Okay, let's have more lights on Zaitsev rule in elimination reactions. The more highly substituted alkene is, the product predominates. Okay, and stability of alkenes. This is the order of the Zaitsev rule. You can see the highly substituted alkane is the tetra substituted. Student, keep remember, I just wrote methyl for the sake of this simplicity. This Me, you can consider any alkyl group. It could be ethyl, propyl, pentyl, hexyl, vice versa. But just for the sake of the simplicity, I wrote if you have an alkane and this alkane is bonded with four alkyl group. So this alkene is known as tetra-alkylated alkene, and this is the most stable one because of the uh, hyperconjugation or the resonance effect, vice versa. And similarly, the second highest alkene or second highest stable alkene is the tri-alkylated. You can see there are three alkyl group, and the third stable alkene is the trans alkene, trans dialkylated. You can see this is trans, one up, one down, and this is the alkene. Fourth stable one, the cis alkene and cis dialkylated, and the least one is the monoalkylated alkene. And we have another least one, simple unsubstituted alkene is the least stable one. Okay. Do you think, student, that do you think really think that always the formation of alkene follow or favor the Zaitsev rule? Do you think really it's fine? Okay, let's look at these example. For example, if you use or you wanted to do the dehydrohalogenation by using the sterically bulky base. A question was asked to me, what do you mean by the sterically bulky base or simple the bulky base? Bulky base means the most substituted base. You can see this carbon bonded with three alkyl group. And of course, because of this oxyanion, this is the base. So this is the most substituted alkene. That's why it is known as the bulky base. This type of the base favor the formation of less substituted alkene. Definitely, this base cannot eliminate the proton from between the carbon chain. So this type of the base can easily deprotonate any alkyl halide from the less hindered side. For example, this is what basically the opposite of the Zaitsev rule. And once you will use alkyl halide with this base, you will have basically the anti-Zaitsev product. And this is known as basically the Hoffman rule. And the product will form is also known as the Hoffman product. Okay. For example, let us see some specific example. This is basically you have a 2-bromo butane, and see carefully on right side, this is CH3, I share it with the pink color. On left side you have a CH2 shaded with the blue color. Both are basically attached with the beta carbon, and that's why known as the beta hydrogen. Once you will use the small base, a small base can eliminate the proton easily in between the carbon. And a small base will predominantly give you the most substituted alkene in high yield. This is basically 2-butene, and this is the dialkylated alkene in 80% yield. And similarly, once you will use the small base, it will give you 1 butane in a less concentration or less yield, because this is the Zaitsev rule, and according to the Zaitsev rule, high substituted alkene will be the major product. And similarly, once you will use the potassium tertiary BuOK or simply the BuOK base, a bulky base. For bulky base, it is difficult to deprotonate inside the carbon chain. So easily this bulky base will remove this proton. And by this way, this bulky base once will remove this proton, it is the major product. You can see the removal of this proton will give you the one butene. And 1 butene, by using a bulky base, you will have the more product. And the less substituted alkene using this bulky base is in the less percentage. So this is how a base can change the type of the reaction. Okay, I will show you the same example with basically in dash formula, just to show you the steric hindrance. For example, if you will use the small base, it is definitely can easily remove this proton to give you this corresponding the substitute alkane. And once you will use the bulky base will try to eliminate this proton to give you this uh, unsubstituted alkane in high yield. Okay, now this is some differences, or the you can see the comparison between the Zaitsev rule and the Hoffman rule. For example, here I gave a 2-bromo 2-methyl butane, and once you will use a strong base like sodium ethoxide, when used with this alkyl halide, you will have a high yield of the trialkylated alkene in 69%, and 31 in the less hindered base, means you have 2-methyl butene. Similarly, once you will use the bulky base, the case is reversed. The less hindered alkene is in high percentage because of the steric hindrance, and the most substituted alkene, because of this change in base, you will have the less percentage. So this is how a base can play an important role. Okay, more example. For example, this is a 1 bromo methyl cyclohexane. And of course, because of this is the cyclic alkyl halide, and this carbon is the beta carbon, and the hydrogen attached with this carbon is known as the beta hydrogen. Just for the sake of the simplicity, I wrote Ha and Hb. You can see here this small base can easily deprotonate Ha, because this is the sterically hindered hydrogen, and you have high percentage 91% the substituted alkene, and this alkene is alkylated alkene, one alkyl here, one alkyl here, and one alkyl here. And just 9% the unsubstituted alkene once you are using the strong base or the small base. Similarly, if you are using the bulky base like potassium tertiary butoxide, it will remove this proton rather than this HA. So you can see the percentage of the unsubstituted alkene in 93 percentage. I'm sorry. Okay, now let us see the stereochemistry of the E2 reaction. As I mentioned, this reaction involves at a time 5 atoms in the transition state. Okay, now these all 5 atoms should be in one plane or in the same plane. But how? How they are basically placed in the one plane? This is very important question. These all 5 atoms should be in anticoplanar conformation, prefer the transition state geometry. Now question is, what is anticoplanar? This anticoplanar transition state is basically the staggered position and therefore of lower energy, while the syncoplanar means on the same side removal and at the same time or the similar side of the attack of the base. This transition state is eclipsed. I will show you by means of the example. For example, this is the base and this is the basically three-dimensional arrangement of the alkyl halide. And base remove the proton and this bond will collapse here, and this leaving group, which is basically the alkyl halide, they are basically opposite to each other and they are away from 180 degree almost. So this is the preferred transition state and this is known as the anticoplanar. Of course, they are in a plane, but attacking group and the leaving group, they are on the anti side, the opposite side. Now, if you have a base and remove the proton on the same plane, which is also known as the syncoplanar, this type of the transition state basically have the rigidness or the sterically hindered. So generally E2 do not favor this type of the transition at a transition state and rather than this one. Okay. Orientation, let us look on the orientation of the E2. As I mentioned, that hydrogen and bromine means hydrogen from the definitely from the beta carbon and bromine on the alpha carbon have to be transcoplanar if you have the E2 orientation. If both hydrogen and bromine are cis, similarly the E2 do not favor cis elimination. So this task, how I mention or how to show this hydrogen and bromine as a transcoplanar, which is also known as anti-periplanar. Let us see. For example, this is a cyclohexane derivative, and you have a ethyl, one ethyl, two bromomethyl cyclohexane. And what happened when the strong base like sodium, like ethoxide, remove the proton from this alkyl halide, you have the 100% of this alkene. This is basically a tri-substituted alkene. How? When I draw the cyclic structure or the chair form of the same molecule, this is the cyclic or the chair structure. And you can see here in the chair form of the cyclohexane, you have two type of the bond, the axial bond and the equatorial bond. Axial bond are basically perpendicular. You can see these are the axial bond, and the bond which are on the plane, and these bond are known as the equatorial bond. Now you can see this bromine has two type of hydrogen with red and hydrogen with blue. Blue is anti-periplanar to this one. You can see once the base will remove this proton, of course this bond will shift here, which result in the removal of the bromine R. Now this hydrogen red is actually um, this is a syncoplanar, and E2 reaction do not favor the removal of HBr by the passion of syn coplanar. So this is generally will not proceeded while this removal of hydrogen is proceeded, which is the trans coplanar. Okay, here's some more example. In this case, this is the alkyl halide. Now this alkyl or this halogen or this the chlorine only, of course this chlorine and this hydrogen, they are syn coplanar, means on the same side, while this hydrogen and this chlorine, they are anti coplanar. Once the base will attack, the base will remove this proton, which result, you can see here the base is removing this proton, which is the anti periplanar, which result in the removal of this halogen to give you this corresponding alkane, and which is in, of course, in the 100% yield. Come to the E1 reaction. E1 reaction, also known as elimination unimolecular reaction. Definitely, just like SN1 reaction, this reaction occurs in tertiary alkyl halide. Okay, of course, this is basically a two-step reaction, and the rate depends on the concentration of the alkyl halide. First step is the formation of the carbocation, which is also known as a rate determining step, or which is the slow step. And you can see here, this is basically a carbon which having the positive charge after the removal of the halogen, and after this carbon is known as the beta carbon, and the hydrogen is known as the beta hydrogen. Okay, and in the second step, which is the fast step, a nucleophile will attack, or the base will remove this proton to make this double bond between this carbon, which is the fast one. Okay, as I mentioned, just like SN1 reaction, E1 also in two steps. The first step is basically the removal of the halogen to give this carbocation, which is the rate determining step, and that's basically I already explained. And the second step, which is the fast one, to give you this corresponding alkane. Okay, by this. So now very important point. Let us see the competition between E1 and SN1. How we can distinguish both E1 and SN1 occur in tertiary alkyl halide. Now, how we can identify when E1 occur, when SN1 occur? Okay, does H2O act like a nucleophile or the base? How we can distinguish? Let us see. For example, if you have this, tertiary butyl chloride, and you are using a water molecule, it could be as a nucleophile or as a base. So what happened? We already know that tertiary alkyl halide generally favor the formation of the carbocation. Okay, now if water molecule is acting as a nucleophile, this will result in the substitution reaction, like in this way. So water is a good nucleophile rather than a base, okay, which basically giving you the substituted product. Okay, and you have a small percentage of the corresponding alkene if water is acting as a base. Definitely, once you treat a tertiary butyl chloride with water molecule as a base or as a nucleophile, you have a mixture of product. In this case, the mixture of product, you have high yield of substituted product, which is the SN, which is formed by means of the SN1 reaction, and you have the less yield of alkene. Okay, now how to favor an E2 mechanism? I will show you step by step. When you are using a secondary or tertiary alkyl halide, if possible, and because of the steric hindrance in the substrate, it will inhibit the substitution and it will favor the elimination reaction. Okay, when a synthesis must begin with a primary alkyl halide. We have to use a bulky base because the steric hindrance of the bulky base will inhibit the substitution. Okay, and always use a high concentration of the strong and non-polarizable base such as an alkoxide. You know, when we have a weak or the polarized base, it would not drive the reaction toward a bimolecular reaction, actually allowing unimolecular process such as an SN1 or even reaction to complete. I will show you by means of the example in the next slide. Sodium ethoxide in ethanol and potassium tertiary butoxide in tertiary butyl alcohol are bases typically used to promote E2 reaction rather than SN2 reaction. Keep remember, bulky base will give you the elimination reaction rather than the substitution reaction. Okay, and at high temperature, heat generally favor elimination over substitution. Keep remember, once you are heating any alkyl halide in the presence of the base, it will favor elimination reaction rather than substitution reaction. It is very important point. Okay, now let us begin the competition of elimination and substitution with more example. How to determine? I have already explained so many points. Now apply these points over on the example. How to determine whether substitution or elimination is favored? See, this is the alkyl halide. This carbon is bonded with this halogen. Of course, this is alpha carbon and this is beta carbon and this is the beta hydrogen. Once nucleophile attack at this carbon, and you have this removal of this halogen, of course this is SN2 reaction, definitely is a substitution. And similarly you have this one, and once nucleophile abstract this proton, this bond will collapse here, which result in the removal of the halogen, and then you have the elimination. This is E2 reaction. This is how we know, and this is how happen in these reactions. This is a very general reaction. Now what happened if we have a primary substrate, or we can say we have a primary alkyl halide, and we are treating primary alkyl halide with a strong base, e.g. for example sodium ethoxide. Here I just wrote the ethoxide. Now this small base with primary substrate favor SN2 reaction. Definitely major product will be for SN2 reaction, substitution product, and of course we have minor product as an elimination one. Okay, see for example, this is the alkyl halide, or we have a 2-bromobutane, and this is the small base. This is a small base will substitute. Okay, and you have an ether SN2, 90% yield, while elimination product is just 10%. Of course in elimination beta hydrogen remove and this halogen will remove, and you have this double bond here, just 10%. Similarly, if you are using a secondary substrate with strong base, in previous example we have the primary alkyl halide. Now in this example I am using the basically secondary alkyl halide. Secondary alkyl halide with a strong base favor elimination. It is opposite with the primary alkyl halide. Okay, in primary alkyl halide, when we are using the strong base, we have the substituted product in the high yield. While if you are using secondary alkyl halide and treating with a strong base, you have the major product of elimination one, and substituted product you have in less percentage, like 20%. Okay, now see, once you are using a 3-degree or tertiary substrate with the strong base, you can see that we are just changing the substrate. Substrate means alkyl halide. Base is same. In the first case, we have the primary alkyl halide. In the second previous example, we have the secondary alkyl halide. Now, in this case, we have a tertiary alkyl halide. So, imagine once you are using tertiary alkyl halide with the similar strong base, it is also favored elimination reaction. You can see this is in 91%. When we have a 2-bromo 2-methyl propane with a strong base, 91% you have the elimination product, while just 9% you have the substituted product, right? Very important point. Increasing the temperature also favor elimination even more. Mean maybe if you increase the temperature, you have less percentage of the substituted one, or you can increase more than 91 percentage. Okay. Here are very small differences between a base and a nucleophile. It will help you a lot. You also know the differences between them as well. Okay, what is base? Unhindered, a small base nucleophile, favored SN2 reaction. For example, this is the small base methoxide, and this is small. This small base, once reacted with the primary alkyl halide, it always favored SN2 reaction, already mentioned. Okay, hindered bulky base or a nucleophile always favor E2 reaction. Okay, this is the basically same substrate, just changing the base. Here the small base, here the bulky base. This bulky base favor elimination reaction. Okay, and you have a less percentage yield of the substitution reaction. Already explained in the previous slides. What do you mean by the bulky base? Now here one more favor, the one more difference is the basicity and polarization. Polarization means the delocalization of the electron. This also favor the SN2 reaction. Once you are using a weak base or the polarized base, weak base actually act as a nucleophile to give you the nucleophilic substitution reaction, and in this case you have 0% of the elimination. And similarly, if you have the secondary alkyl halide treat with the strong base, you have somehow the mixture. Of course, high yield will be of the elimination product. Okay, tertiary halides. What happened? What is the competition between SN1 or E1 or E2? What happened in this case once you are using a tertiary halide? Tertiary halide. If you are using the strong base already mentioned, it favors the elimination rather than SN1 reaction, 100% of the elimination. But if you are using a solvent and only heat you are providing, you will have the mixture of E1, E2, and SN1. So see, heat can change the dramatic change in the product. All right, that's all of today's lecture. Hope to enjoy the other online lecture as well.